So I just want to look a little bit in more detail at this thing called lattice enthalpy or lattice energy. Let's just do some comparisons, shall we? So the lattice enthalpy for sodium chloride is 786. What are we talking about here? Well, if it was the lattice dissociation enthalpy, it would be plus 786. If it was the lattice formation enthalpy, it would be minus 786, but it's still the same number. Let's compare that with sodium bromide and sodium iodide. What happens as we go down the group? Well, the number gets smaller. So why is that? Well, the only thing we've changed is the halide ion there. As the ion gets larger, so the size of the ion increases, the lattice energy decreases. That's a great time for that pen to run out. And why is that? Well, it's simply because, let's get a couple of colours going. The let's put some pluses in. The ions can get closer together if they're all about the same size. If we put in a positive ion with a large negative ion, let's accentuate it a bit here, and the ions are just a little bit further apart, which means it's easier to pull them apart, which means the lattice energy decreases. So the size of ion increases, the lattice energy decreases there. Just see if I've got another pen. Oops. Bane of a teacher's life, isn't it? Running out of a board pen midway through a lesson. Okay. What about if we compare it with, what else have I got here? It's a little bit crummy, but it's working. Magnesium oxide. Well, magnesium oxide has a lattice enthalpy of 3795. That's quite a big number. So what's going on there? Well, we've done a couple of things there. We've changed both ions, obviously. They both have a 2 charge on, magnesium 2 plus, oxide 2 minus. So by increasing the charge of the ion, we see a huge increase in lattice energy. For hopefully fairly obvious reasons. A larger charge on the ion means more attractive forces. Of course, Mg2 plus is also smaller than Na plus. I mean, the magnesium atom is smaller than sodium anyway because it's got a larger nuclear charge which has a stronger hold on the electron cloud. But we've taken 2 electrons away from magnesium and only 1 away from sodium. They actually have the same number of electrons, but magnesium has a higher nuclear charge and is hanging on to those electrons much more tightly. So we've got a smaller ion there as well. So smaller ion means more attraction, and the charge on the ion means more attraction. So we've got a big difference there. Okay, hopefully that's relatively straightforward. This next bit might not be. When we were in year 10, probably, we talked about how you've got metals and non-metals, and if you have metals and non-metals bonding together, then you get an ionic bond, and if you have non-metals and non-metals bonding together, then you get a covalent bond. It's not quite as simple as that. Really, these are 2 extremes on the end of a continuum. If we put in the remaining atoms here, going across that period, then sodium's the most electropositive or the least electronegative, chlorine's the most electronegative. If we put chlorine with chlorine, of course it's got a perfect share of the electrons because the electrons are perfectly shared, is what I should have said. because they're both the same atom with the same electronegativity. But if I had phosphorus bonded with chlorine, well, then of course we've got chlorine is more electronegative, and that would give the chlorine a greater share of the electrons than the phosphorus. It's still covalent, but with some ionic character. Silicon chloride is covalent as well, but what about aluminium chloride? Well, aluminium's a metal and chlorine's a non-metal, so you'd expect it to be aluminium having a charge and chloride having a charge, but there's not a bigger difference in electronegativity for aluminium chlorine as there is for sodium and chlorine, so there'll be some covalent character. So what we could say is as we go across the group, there's an increase in covalent character. So it's possible to have an ionic compound with some covalent character. In the same way, it's possible to have a covalent compound with some ionic character. It's not quite as cut and dry as some things are ionic and other things are covalent. Now, with that in mind, let's look at some values here for sodium chloride. What we have first of all is the experimental values for lattice energy, in other words, using a Born-Haber cycle. We've measured all the ionization energy and the atomization energy, and we've come through with a value for the lattice formation enthalpy of minus 786. Now, it's also possible to get a theoretical value using what's called the ionic model, or the perfect ionic model. What's that? Well, that's basically getting the physicists to go to first principles and say, okay, if I had a positively charged sphere and a negatively charged sphere and they were such and such a distance apart and they've got these attractive forces, how much energy would it take to pull them apart? And that's something the physicists, God bless them, can do for us. And they would say, in theory, the ionization enthalpy, the lattice dissociation enthalpy, the lattice formation enthalpy for sodium chloride will be 766. So what? Well, these values are pretty close to being equal. They differ by, well, it's not very much, is it? 20. It's about 1%, 2%. It's pretty small. So that tells us that sodium chloride is more or less made up of spheres with no covalent character at all. But if I now compare that with MgI2 here, just using the values in the book, again, the experimental value using the Born-Haber cycle gives us a value of 2327. But if we get the physicists to come up with a theoretical model, it's minus 1944. Now, they do not agree at all. They differ by nearly 20%. And notice that the experimental model is much higher than the theoretical model. It's a stronger bond between the magnesium and the iodine that we'd expect if we just imagine them to be perfectly spherical ions. So what that tells us is magnesium iodide does not conform to the perfect ionic model. It must have some covalent character. In other words, that extra bit of bonding between 1944 and 2327, there's more bonding there than we'd expect, tells us that there's more going on than just ionic bonding. So magnesium iodide excuse me, has some covalent character. Why? Well, because it doesn't have perfectly spherical ions. And the reason for that is that excuse me, magnesium ions are small, highly charged ions. small, high charge ions. Iodide ions are large. And what that means is that the magnesium ions are very polarizing. They have strong attractive forces on neighbouring ions. The iodide ions are more easily polarized because they're large and floppy and they can flab around a little bit in several directions. They're like a sort of big squashy ball that can be distorted in different directions by small, highly charged ions there. So if we've got large ions next to small ions, we'd expect an appreciable amount of covalent character because the ions are distorted. Another example would be silver chloride. Silver, being a larger atom, forms larger ions, and therefore we'd get an appreciable amount of covalent character in silver chloride, much more so than perky little sodium chloride over there. Okay, I hope some of that made sense. And, if it didn't, hey, just watch the video again. Top tip.